I call on the next speaker. Now we are moving from very old stars, like the RL stars, to very young stars, like Hunting for Outbursting Young Stars, the Hoist project by Dirk Froebrich. Dirk.
Thank you. Okay, thank you very much for the introduction and for letting me introduce our Hoist project, which stands for Hunting Outbursting Young Stars. That's what it originally was invented for. And what I'm here to tell you today is basically what me and two colleagues, Dr. Alex Scholz and Dr. Justin Campbell-White, who are the kind of the scientific leads of the project, are what we actually do with the data, because I'll show you in a minute that just going for the outbursting young stars gets quite boring quite quickly, and no one wants to really participate in that. So what I'll do a bit is I'll give you a little bit of background on the science, why we are doing these things, what we're trying to find out, the goals of our project, show you some results in the middle of the talk that might or might not be quite long, and then at the end a little bit on how to participate in the project if you so wish. So the science background is really star formation. This is a sketch you all have seen kind of one way or another, so I'm not going to really talk about this. But what we are really interested in is these phases where you have that central object, which eventually will be the star, that's still surrounded by a disk of material, which is actively accreting material onto the star. There's jets coming out. And we are really interested in what happens on these, in the very inner parts of these accretion disks, where eventually you will actually form the planetary systems. Right, so we're trying to understand kind of the end of the accretion phase onto the star and the beginning of the planet formation process in these disks. That is the main idea. And in the very inner bits, there's a lot of things going on. So we have the central star that has magnetic fields, which are linked to a gaseous disk in the center, simply because the radiation from the central object destroys all the dust that you can get in the disk. And in terms of size scales, so that inner bit where we only have gas, it's about kind of the order of 10 times the radius of the star or the radius of the sun. So to put that in perspective, further out, when it gets cold enough, you get dust in these disks. And typically, these disks, the picture here is nice and smooth. It's probably way more turbulent. The density is not really nicely distributed azimuthally around the star, which helps to cause a lot of variability in the system, because there's a lot of things that happen. So the material flows onto the star, that creates some of the luminosity of that. That mass flow changes, so the star's luminosity changes. If you look from the right angle, you have to look through some of the disk in the system. That, of course, orbits following Kepler's third law around the star, and then the amount of material along your line of sight keeps constantly changing. Again, that makes the star variable. So basically, by definition, all the young stars vary, which is quite interesting, and many of them are not periodic. So you can keep looking at them forever, and you don't know what they're going to do next. So this is just to give you an idea of the different kinds of variabilities that we have in the young stars in terms of the time scale, how long these things last. So kind of useful units are on the top, and the y-axis just tells you by how much does the brightness really change. So there's a lot of things that are related to the change in the mass accretion rate, these kind of bursts here of the different prototypes. And you can see they range from things that happen on timescales of days all the way to hundreds of years for these very big F-Ori outbursts, which we tried to identify basically with that project. But the problem is not that these things also only last, they last very long, up to maybe 100 years or so. They're also extremely rare. So typically on a given star, that will probably happen only once every 50,000 years or so. So it's quite hard to actually find them. In particular, these objects, probably one of the least membered classes of variables. We only know about 25 of those in total. So we still haven't really understood how they work. There's a couple of other things that can happen. So material moving in or out of the line of sight. These are all these things in red, where you basically have different kind of mechanisms that causes the star to fade by certain amounts. And then we have star spots, eclipsing binaries. The next talk will talk about the star spots in particular. So basically, if you want to, what we want to do is really observe all these things, all these objects in one project. So you need to cover quite a large range in terms of timescales and also in terms of accuracy. So it's very easy to see these kind of things. You don't need precision. You can do that with the naked eye if you have a couple of binoculars. But if you want to kind of investigate these things at the bottom, you need quite accurate photometry. So one of the things we basically do is we study the structure of the disk. So if something is sticking out of the disk, and let's say the material is moving to the right here in front of the star, this structure eventually might move in front of the central object, and the central object will dim. It also changes its color. Scattering of the dust basically scatters more of the blue light, so change the color. And we can, in essence, use this to measure the structure in these disks along the direction of motion in front of the star. And that's much more accurate than what you can do with direct imaging or interferometry. So if you use ALMA or VLT, the best resolution is 0.025 arc seconds. And if you work out how much is that in terms of real physical distance in some of those disks, if you go to the nearest young stars, that's 5 astronomical units. You can't get a handle on any better detail in those disks nowadays, even with ALMA. And VLTI, using gravity, you're a factor of 10 better. That's half or so of an astronomical unit. But you can only do that for the nearest young stars and probably a handful. And then everybody else wants to do something else with this instrument. This kind of monitoring, where you simply monitor, you measure how long does one of these eclipses take, or how quickly does the eclipse set on, that's independent of the distance of that object, as long as you can see it. And the size resolution you get is basically the size of your light source, the light of the star, which is 2% or 1% of the astronomical unit. So it's much, much better. Of course, you only have the resolution in one direction. You can't make a picture. And of course, we can also look onto the surface of the star, but the next talk is going to talk about that in a bit more detail, so it's just going to skip over that. Hence, our main goals are basically looking at the structure of these accretion disks at high resolution by monitoring them, and also looking at the surface of these stars in detail. So how are we going to do this? Well, we're trying to basically monitor things for maybe 25, 30 years, once a day, hopefully twice a day, every 12 hours or so, in multiple filters. So no professional observatory will allow you to do that. But if you pick the right stars, they're all bright enough for small telescopes. So that's hence where the project came about. We want to do 2 observations a day, preferably 12 hours apart, so we need people all over the world in all the optical filters we can get hold of, including H-alpha. And what we've done is we've selected young clusters of stars. To basically every picture covers a couple of hundred young stars in one go. They're all nearby, less than a kiloparsec or 3,000 light years, which basically makes the sun the 15th magnitude star. So that is reasonably easy to do. So we can do this with these small telescopes. And we started this, here are some of the targets, and they're all pretty. That's the other thing. Everybody takes pictures of these objects anyway, even if you are not really doing photometry. If you do take pictures to make nice pictures, then you're very welcome to keep doing that. All I want your pictures. So you don't actually have to do any of the measurements. That's something I'm going to point out later. We do everything. All we're interested in is the FITS files of your observations. So here are our observers on some maps. I think Josh's one is somewhere there. Which one are you? The one on the top, right? Yes. But because we started in the UK, there's a lot of people in the UK. The weather's not really great. We have a lot of people in Spain, and then distributed some in the US already. We've now gathered, we have about 100 people who've taken images from 15 countries, 85,000 or so images that we have now in the database. And in those images, we measure the brightness of every single star because we do not know which one is going to be the one that starts varying soon. So we have over 300 million brightness measurements which we can analyze. There's about 3,000 young stars in all these fields that we have, where we have good light curves already for. So a couple of examples of what we've done. We can measure periodicity and spots. That's the next talk, so I'm going to skip over that. But what you can also do is we can look at the variability itself. It's completely random what these objects do, because there's material in different radii in the disk. It moves at different velocities. So what you can do is you can make a diagram for every single star where basically once you have enough data, you can basically ask the question, what's the probability if I observe that star on 2 occasions, a given time t apart, that's the x-axis here, what's the probability that it changes by a certain amount? Right? If it doesn't change, it's here at 0. And for this star, it mostly doesn't change, whatever time I have between my observations. But there's a small chance that this star changes by certain amounts over certain timescales. And so we have these fingerprints, as we call them, because it's different for every single star. For every light curve we have, it looks slightly different. And we're trying to find out, can we somehow group these stars together? Do these variability behaviors really depend on the properties of the star, the mass, the age, or something like that. So we have a new student starting to do this quite soon. I think I have a couple of examples. There's 3 objects here somewhere in Orion, and you can see, if you can do that for different filters, that they really differ. So this one doesn't vary a lot. This one is quite variable. Even at quite short time scales of maybe 10 or so days. So there's quite a lot of things to look at. And typically, if you go to the shorter wavelength filters, the variability typically increases. We all know that the stars are more variable if you go to shorter wavelengths. What else we can do? We've started to analyze the entire sample of the young stars we have. One of the things you can do, you can ask how many of these stars still have a disk around them. So if you have a cluster, this so-called disk fraction is usually used to calculate the age of that cluster, because getting the age even of a young embedded cluster is reasonably tricky. So people tend to use the fraction of objects that have a disk. That requires observations at a mid-infrared with satellites to actually work this out. And what I've done is I've simply plotted that fraction of disks against the fraction of stars I found to be variable in that cluster. And you get a pretty decent correlation. Hence, instead of using the disk fraction, you can use the fraction of stars, which is variable. There are some exceptions. We need to work out why, what is special about these. The circled size, by the way, is simply the number of stars in each of those clusters. So the big cluster, the big circle here, that's the Orion Nebula, because it has a lot of stars in it. But it's quite a nice correlation that we have. You can do other fun things with all the individual light curves. You can basically work out, if you have a light curve, is the star a outbursting object? So is it basically the light curve flat and then has humps towards brighter magnitudes? Or is it a burst, or is it a dipper? I.e., is the light curve flat and then it has dimming events? So you can basically calculate a property, which we call the asymmetry index, for every single light curve. And also, you can look, is the variability periodic? Is it strictly periodic? Then it gets a 0. Is it completely random? Is the variation completely random? Then it's stochastic, and then the light curve ends on the right. And then you can just plot all these points, and you see, well, most of the objects are more or less stochastic, and you get dimming events, dipping events. And one of the things we're trying to find out, which we haven't done yet, is for every cluster, what fraction is dippers, what fraction are outbursting objects, what fraction are actually periodic objects, which have periodic variability due to spots, for example. So that is one thing that we are going to do. I played a little bit around. We have for the periodic objects, which are basically the rotation period of these stars, you can ask, if I plot those, what is the likelihood that they have a disk around them? So objects on the top, they are clear evidence. There's a disk around them. The objects at the bottom here below half, they have no disk close to the star. And what you can see is, or if you trust me on that, for the objects that do not have an inner disk, there's a larger fraction with short rotation periods compared to the longer rotation periods. If you make this as a dividing line, for the objects that have a disk, more of them actually have a longer rotation period. We can understand that because the magnetic field ties the star to the disk itself. And the disk can't be slowed down, so Kepler's laws always apply. But once that connection disappears, the star can basically shrink and start to spin faster due to the conservation of angular momentum. So these are some things we are trying to do. Then we have these, you might have heard of these AA tau stars, where you have a warped inner disk, which comes from the misalignment of the rotation axis of the central star and the rotation axis of the disk. And the magnetic field again kind of warps the disk on one side to the top and the other side at the bottom. And if you then look from the right angle, you get a periodic modulation of this of the light curve. And this is one such object where, if you look very carefully, this is data from our university telescope over a couple of years, you see about a 1 month periodic dimming event. So every 30 days the object gets fainter. So this is the light curve you get actually from the project for that. So we have a lot of people observe this just for a couple of months, where again you can see much more detail on what's going on. And the interesting thing with this object is the period is actually too long to be one of those AA taus, because the period of about 30 days means the object, or the warp that is moving about, that is about 0.15 astronomical units from the star, and the magnetic fields are not strong enough at that distance to actually do the warping. They're going to be too small. So there needs to be another reason for that warp, and the only kind of sensible solution is that somewhere in that system there's a planet that has a slight inclination. This is way too exaggerated compared to the main disk. And if you do that, that planet with its orbit will warp or tilt the inner part of the accretion disk. And then we're still looking in this direction. And then again, periodically, we have the object, or the dust basically occulting the central object and making the system fainter. So it's some indirect evidence for a planet. So direct evidence is very hard. So we've seen all these exoplanet light curves. This is just a random one we made. You need very high accuracy photometry, right? So millimagnitudes to see the transit. Our data is typically more noisy. We're talking 2 or 3% because it's very diverse. So we can't do that. But if you have a young planet around that planet, even in the solar system, there's an area around each planet called the Hill sphere, where the material is gravitationally bound to the planet. So in a young system, that's the area out of the disk. The planet will basically keep accreting. So that part can be filled with gas and dust from the disk that is slowly accreting onto the planet. And so Jupiter probably had one of its own little disks, right? It looks like its own solar system. And the size of that Hill sphere is as easily determined by simply the mass ratio between the star and the planet itself. And you can do some experiments. You just put Jupiter at half an astronomical unit from the sun. And then you work out what's the size of the Hill sphere. And that's actually bigger than the star itself. So that increases the chance of an occultation. It's much bigger than the planet. And secondly, you can actually make quite deep transits if a large fraction of that Hill sphere is full of material. So you can try to find these occulting Hill spheres instead of the protoplanet itself. There's one candidate where we have something. So what I've plotted on the bottom is not time, but number of periods, where the period is 182 days. So every solid line is basically one period. And for most of them, there is a deep dimming event. So some are missing. We don't know why. Not all the Hill sphere is probably full of material. And if it's not a perfect alignment, that might be the case. So green, again, that's our data. And red and blue are some previous data sets. I think that's punt stars here. And even there, you can see the two transits happening. So that's a good candidate, but we need some kind of more detailed analysis for that. And the last example, if you're interested in things that are not young, massive, outbursting BE stars, again, the sample contains some of these regular bursting BE stars, which are quite interesting because we don't really know how these outbursts actually come about in detail. And to really observe them, you need to know when this outburst starts, at least, and they're typically completely irregular. So we found a couple which are almost periodic. The amplitude changes, you can see these humps here. Some of them are very small, some are missing, but they're pretty regular in terms of periodicity. We didn't aim for those, they just happen to be in the same field. So there's a lot of things we can do, and then we can even model these things. To end the talk, a little bit about if you want to participate, what you need. Basically not much. You need a telescope, of course, with a camera, but 2-inch telescope is good enough. You have data with a 5-centimeter telescope that is useful. Camera, any you want, CMOS, CCD, DSLR. DSLR is actually great. You get 3 filters at the same time. What we need is basically some observations through a filter. No clear observations. We need the color data. Pixel scale, preferably less than 3 arcseconds. Simply, some fields are in the galactic plane. We're trying to separate the stars out. That helps. Any field of view will do. There's some targets which are very, they don't have a lot of stars, especially at the shorter wavelengths, so a small field of view there is not really useful. But any optical filter from the U to the I band will do, including the narrow band H alpha. We look for that. And what we actually take is the FITS images, and the only information that we really take is the date and the time of the observation, naturally. The filter you've used, we take that out, and the exposure time as well. We don't use that for anything other than statistics, so if that's wrong, it doesn't matter. Once you've done that, you can spend as much time, of course, on the observations as you like. Observations up to thin cirrus is okay. We have people who observe almost from central London. The faint stars are missing, doesn't really matter. We measure everything we can see in the picture. Observing strategy, if you have a limited amount of time, what we prefer is you take the same target in multiple filters. That's more useful than 5 targets in the same filter, because we're interested in the colors of the stars and how they change. So all we ask you to do is apply a basic data reduction, dark flat fields bias. If you have more than 1 image per filter per night, please stack them up. We're not interested in short-term variability, less than 12 hours or so. And then you can submit them to our database. There's some help videos on YouTube how to go about that. Or come to me and talk to me, then we help you with setting this up. There's a bit of processing to do. The last thing I want to mention is we also do some kind of educational work. So we are a global Sky partner with Delos Campus Observatory. It's an educational program. So we work with teachers and pupils and other amateurs, basically give them data on remote telescopes if you don't have your own, to learn basically how to use those. And then there are tutorials how to access and analyze our data. The data is public straight away, unless the database is broken. Those people who know about our problems over the last 2 months will know that. And of course, you get co-authorship if you include your data in the paper. It's written online, so at any time you can actually look what we are doing. You don't just get the ready-made version. We usually ask you to write a little section on your own telescope to be included somewhere. And of course, we offer talks. So if you are a member of a society that would like me to give a talk, either in person or online, or someone else from the team, then we can do that. So that's it. There's our 3 science leads. Thanks to all the participants, including, I think there's 3 at least here. Josh, there you are, and someone else. Where's the guy in the yellow shirt? He's disappeared. So there's 3 people in the room who have given data, and so all the information is on the website. There's some social media. Thank you very much.
Thank you, Dirk, for this overview talk about the Hoist project, and hopefully some of the audience will join the project. It's open for questions, discussion.
Do you require a photometry filter? Because you were saying you take a picture of people doing imaging. Imaging filter have a rectangular response over color, you know. Photometry filters are sort of triangular. Do you specify photometry filters?
No. So in principle, any filter that is close, somehow resembling something like a UBVRI will do. So we have so much data now, we can correct all the color terms for all the filters, because what we do in the background is we identified for every field all the stars that do not vary, because we have 10 years of data now almost, so we know which stars do not change. We know their color and their brightness. And then for every picture that comes in, we calibrate that based on that knowledge.
Thank you for a presentation of this interesting project. I will continue the line Eve asked. What are the challenges of processing data from all those different setups and different conditions and different observers? Because that must be a lot of work.
Yeah, so as I said, once we now have a lot of data, so we can, for every image, we can determine the color term, which can come from slightly different filters and slightly different observing conditions, right? Thin cirrus makes a color term in your data. That is basically solved. The main problem that remains, which we will not be able to fix, is the different pixel scales and different resolutions. So when we pull out light curves for stars where there's 2 stars close together, because for every data point we of course store the full width of maximum of every measurement. So if you analyze stars in a close, even a parent binary system that is 5 arcseconds apart, then you simply, there's one query in the database that removes everything that comes back that has a resolution that's too bad, and then you're done with that. So because we have stored all the information, it's then on the data analysis side where we can, for example, just remove, if the error bar is too big, let's say if you want to do spot measurements, you need high accuracy photometry, we can remove all those. If there's a nearby star, you don't want anything where the full width of maximum is worse than 3 arcseconds, and you can automatically exclude those. So yeah, it took a long time to get to that stage, but once you have enough data, it's amazing what you can do.
Indeed. I saw few projects who failed doing that. So good work.
One more question. If not, we thank Dirk again.